Good day, everyone. Welcome once again to our session for today. Before we go to our next example, I would like to show you again our solution last time, no? For our example number 5. Okay, so this is our example number 5 last time. I forgot to write the requirement class for S. So we have two requirements, that is the final velocity and also the this question. To answer this question, how far will he fall? So that refers to the displacement. Okay, this one. And last time we solved for the final velocity using this third formula. Actually, we can also use the first formula class, no? This one. So using this formula to calculate for the final velocity, so we have here. Okay, you get the same result. Alright, so this is our complete solution for this problem, example number 5. Okay, now let's proceed to our next example. So our example number 6. Alright, so we have here the problem. Problem number 6. If Michael Jordan has a vertical leap of 1.29 meters, then what is his takeoff speed and his hang time? Hang time means the total time to move upward to the peak and then return to the ground. Okay, so that's the problem number 5. Number 6, example number 6. Okay, so we are given here the vertical leap of 1.29 meters. So what does it mean? So it means that assuming this is the ground. Okay, so at t equal to 0, so at t equal to 0, so at time t equal to 0 here, so it means that Michael Jordan is not yet moving, so the initial velocity is equal to 0. And as he moves or run towards the, for example, to the ring. Okay, so assuming at this point here, so let this be time, so a time t. So we don't know what is the time yet, no? So at certain time at this point where he begin his vertical lift. Okay, so from here to the vertical leap. Alright, so it means that as he moves from this point to this point, he's running and then make a vertical leap. So we have here the initial velocity, so at this point at t equal to t, so this is our v. So this is the velocity where he leapt vertically. Alright, before we continue with that, let's write down first the given. So we're given here the vertical leap, so it means that this height here, that's this height here, so this is the s. So that's given in the problem. Our s is equal to 1.29 meters. Okay, so what else are given? So none. Then we are required to solve for the, so it says that what is his takeoff speed. So takeoff speed, it refers to our final velocity v here. So we are required to solve for the final velocity. So what is this velocity? And his hang time. So total hang time. Okay, so total time to move upward to the peak and then return to the ground. So we can call this as t total. So the time that so the time that he goes up, so going up, so we can call this as T1, and then so the time that he returns to the ground, so we will call this as T2. Okay, so therefore our total time is equal to T1 plus T2. So we have to solve for this total time. Okay, so for our solution, so we'll use, so what formula shall we use? So write down first the formulas. So we have final velocity is equal to the initial velocity plus acceleration times time. And the other one is we have the displacement s equal to initial velocity times time plus 1/2 a times acceleration times time squared. And finally we have the square of the final velocity equal to the initial velocity square plus twice the product of the acceleration and the displacement. So as we know that at t equal to 0, at t equal to 0, so we have initial velocity is equal to 0 as well. So therefore we have we can use this formula. So v squared equal to 2as. And solving for the final velocity, v is equal to, so taking square root on both sides, so square root of v squared is v, then we have the square root of 2 times s. So substituting the values, so v is equal to the square root of 2 times RA is, what is RA? So again, this is related to free fall. So our acceleration here, that is the gravitational acceleration. Alright, so our A here, so our A is the gravitational acceleration, and that is equal to 9.81 meter per second squared. And we'll use that constant. Okay, so 2 times 9.81 and multiplied by s is the displacement that is given as 1.29 meters. Okay, so when you manipulate the given units, so what is left here is just the meters, because we have 9.81 meter per second squared. Okay, and here we have meter, so meter and meter squared, square root of meter squared is meter. Then you have denominator for this one is 9.81 meter per second squared. Second squared, square root of second squared is second, so that's why we have the unit in terms of meter per second. So using your calculator, we got this final velocity of 5.03 meter per second. Okay, so this is our answer for the velocity. Oh, this is the takeoff speed. Oh, this is the speed that when Michael Jordan takes off. Oh, this velocity here. And to solve for the solving for the total time, so we can use the formula. So we have V equal to VO, or initial velocity, plus the acceleration times t. Alright, so we know that V sub 0 is equal to 0. So we can use this formula class. So this is our velocity, the velocity, final velocity when Michael Jordan takes off. Okay, and then when it reaches at above, so the velocity in going down, so this will be our initial velocity. Okay, initial velocity, which is equal to 0. So we have we can solve for t here. So from here we have t equal to the v divided by a. So t is equal to, we have the velocity calculated here as 5.03 meter per second divided by the gravitational acceleration, which is 9.81 meter per second squared. So meter here and meter here will be equal to 1 when you divide. So we have meter per second divided by we have a meter per second squared. So second squared, we have a second here, will be one factor will be when you divide the second here and also the second at the denominator, and then we have the denominator which is second, so it will go up, so the unit is in terms of second. So time therefore is equal to 0.51 or 0.513 second. Okay, so that's the time. So take note, class, that this is the time when Michael Jordan leap up. Okay, so we get this time, and we can call this time as our T1. Okay, so that will be our time T1. And now for the going down. So when he reaches above and then it goes down, so we can use also this formula. We have S equal to VO, the initial velocity, times time, plus 1/2 times the acceleration times the time, then squared. Okay, so when it goes down, we can use this formula. So here, the initial velocity at this point, so it's like a pre-fall now. So the velocity here is equal to 0. Okay, so this part here becomes 0. This will be equal to 0. So our formula now is S equal to 1/2 A times T squared. And we're given the vertical leap, which is equal to S, and that is equal to 1.29. So equal to 1/2 times the acceleration, which is 9.81, then times T squared. So you see here we have only T as our unknown. So manipulating this one, so you cross multiply 2, then divide both sides by 9.81, then take the square root. So you have t equal to the square root of, so you just cross multiply 2 here, okay? Then after that, divide both sides by 9.81. Then after that, take the square root on both sides. So we have 2 times 1.29 and divided by 9.81. And we got t here, which is equal to 0.513 seconds. Okay, so this is actually our T2. So that's our T2. And then from our formula here, from our analysis, the total time, that is the time when Michael Jordan leap up, make a vertical leap. So it takes him T1 to reach at the top where he stopped going up and then stay for a very short period of time and then goes down. Okay, so that is T1. Then when it goes down, so we have this time T2. So when you add up the hanging or the hang time for Michael Jordan, which is the total time to move upward to the peak and then returns to the ground. So that is the sum of the 2 times, time 1 and time 2. Okay, so therefore the total time or the hang up time T sub T equal to T1 plus T2, which is equal to 0.513 plus 0.513 seconds. So the total time, hang up time, is equal to 1.03 seconds. Okay, so that's all, no? So this is how easy is this problem. Alright, so thank you very much and hope to see you again in our, we still have two more sample problems. Okay, bye for now.